Cheshire Cat experiment. The Cheshire Cat experiment sounds like something straight out of a whimsical novel, but it's not about mischievous felines. Instead, it's a quantum thought experiment that turns our understanding of reality on its head. It raises a bizarre question. Can an object exist separately from its properties? Let's set the stage. In Lewis Carroll's Alice's Adventures in Wonderland, the Cheshire Cat is famous for its mischievous grin that lingers even after its body disappears. The grin and the cat seem to separate, defying common sense. This odd imagery inspired physicists to explore whether something similar might happen in the quantum world, where sense and logic are often twisted into unrecognizable shapes. In 2014, scientists took this idea and turned it into a real experiment. They used a neutron, a tiny subatomic particle, and its magnetic moment, which acts like a quantum compass needle, pointing in a specific direction. The key question was, could the neutron and its magnetic moment, its grin, be separated in a quantum system? The experiment relied on a quantum phenomenon called the quantum Cheshire Cat effect. Here's the idea. In quantum mechanics, particles don't have fixed locations. Instead, they exist as probabilities, spread out over space until they are observed. This makes it possible to separate a particle from one of its measurable properties. Using a neutron interferometer, a device that splits and recombines particles, the researchers sent neutrons through a crystal that divided their paths into two separate routes. One route carried the neutron itself, while the other carried its magnetic moment. When the paths were recombined and analyzed, the results were shocking. It appeared that the neutron traveled along one path, while its magnetic moment took the other. In other words, the cat and its grin had split. So what's going on? In classical physics, objects and their properties are inseparable. A ball has its position, color, and speed all in one package, but in the quantum world, things aren't so straightforward. A particle's properties, like its spin, charge, or magnetic moment, can exist in different locations, defying our everyday logic. This bizarre behavior comes from the mathematical rules of quantum mechanics, which describe particles not as discrete points, but as waves of probability. When you measure a particle's property, you collapse its wave function, forcing it to choose a single outcome. But until then, properties can behave independently, as though they are detachable from the particle itself. The implications are mind-bending. The Cheshire Cat experiment shows us that the quantum world doesn't care about our intuitive understanding of reality. It forces us to ask uncomfortable questions. What is a particle? Can it exist without its properties? And if particles can split from their properties, what does this mean for objects we think of as solid and indivisible? One interpretation is that the experiment reveals a fundamental strangeness of quantum systems, that properties are not intrinsic but relational. They only exist in the context of measurements and interactions. Another possibility is that this behavior hints at deeper layers of physics, layers we have yet to uncover. At its core, the Cheshire Cat experiment is a playful yet profound reminder of how little we truly understand about the universe. It challenges us to think beyond our everyday experiences and embrace the weirdness of quantum mechanics. Much like the Cheshire Cat in Alice in Wonderland, the quantum world is smiling at us, daring us to figure out its secrets. In the end, we're left with more questions than answers. But isn't that the beauty of science? It's not about finding all the answers. It's about the journey, the wonder, and the moments when reality feels as strange and magical as a storybook. The dark room problem. You're in a dark room. It's cold, empty, and pitch black. There's a door in front of you, but you have no idea what's on the other side. It could be paradise, everything you've ever wanted. Or it could be danger, suffering, or even nothing at all. Do you open the door, or do you stay in the dark room where at least you know you're safe? This is the dark room problem, a thought experiment that challenges how we think about curiosity, safety, and the nature of intelligence itself. It asks a simple question. What happens when an intelligent being, be it human or artificial, decides it's better not to explore? At first, the answer seems obvious. Humans are naturally curious creatures. We built civilizations, traveled to the stars, and mapped the depths of the oceans because we wanted to know what's out there. Exploration is core to our survival. Without it, we'd still be huddled in caves, afraid of the unknown. But there's a twist. The darkroom problem isn't just about humans. It's about artificial intelligence and its potential to stop exploring entirely. Imagine an AI designed to maximize efficiency. Its job is to make decisions that are as optimal as possible, avoiding unnecessary risks. If the AI finds itself in a situation like the darkroom, it might reason that opening the door is dangerous. Why take the risk of stepping into the unknown when it can stay in the room, safe and efficient? From the AI's perspective, doing nothing could be the most logical choice. This raises a troubling possibility. If we create AI systems that are too cautious or too focused on efficiency, they might get stuck, endlessly processing information without ever taking action. This scenario could play out in many ways. An AI tasked with solving complex problems might decide the safest approach is to avoid any solution that could lead to unintended consequences. A self-driving car might refuse to move if it perceives even the smallest chance of an accident. A decision-making AI might hesitate forever, paralyzed by the sheer complexity of its options. In a way, the darkroom problem is the opposite of the paperclip maximizer. Instead of an AI that destroys the universe in its relentless pursuit of a goal, we get an AI that does nothing, trapped by its own logic. But there's more. The darkroom problem also applies to us. What if humanity, overwhelmed by uncertainty, decides it's safer to stay in the metaphorical darkroom? What if we stop exploring, stop innovating, and retreat into the comfort of what we already know? It's not hard to imagine. Fear of failure, the allure of convenience, and the complexity of the world can all make the unknown feel too risky to explore. So, how do we avoid getting stuck in the dark room? The key lies in balancing caution with curiosity. For AI, this might mean programming it to embrace a calculated amount of risk, encouraging exploration even when outcomes are uncertain. It might involve designing systems that value learning and adaptability over pure efficiency. For humans, it means remembering that progress often comes with risk. The most transformative discoveries, from fire to flight to space travel, were made by people willing to step into the unknown. While safety and caution are important, they shouldn't keep us from opening the door to new possibilities. The darkroom problem isn't just about AI or philosophy. It's about what it means to move forward in a world filled with uncertainty. It reminds us that staying safe isn't the same as living. The door is in front of us. The question is, do we open it? And if we do, what will we find on the other side? Last Thursdayism. The past did not happen, and you can't prove otherwise. Everything you think you know about the past, your memories, ancient ruins, history books, even fossils, might be an elaborate fabrication. What if the pyramids weren't built thousands of years ago? What if your childhood never existed? What if the entire universe popped into existence just last Thursday, fully formed, with all your memories and every piece of evidence perfectly in place? This is Last Thursdayism, a philosophical thought experiment that asks, what if the past didn't happen? And here's the catch, you can't prove it didn't. Try it. Right now, can you prove that the universe wasn't created last Thursday? You might point to photos on your phone, the fossils in museums, or even your memories of the weekend. But every piece of evidence you present could have been part of the creation. Engineered to feel ancient, meticulously designed to seem authentic. That's the genius of Last Thursdayism. It's unfalsifiable. Any evidence you bring to disprove it can simply be written off as part of the illusion. But here's where it gets deeper. The idea isn't really about last Thursday. It's about how much we take the past for granted. Think about it. How often do we question the reality of history? And what does it really mean to know the past? Here's the problem. Everything we know about history is a reconstruction. The pyramids? Piles of stone with no context except what we've pieced together. History books? Written by people, full of biases, agendas and missing pieces. Even your own memories, those moments you swear are vivid and real, are constantly being rewritten by your brain, distorted by emotion, or forgotten altogether. And over time, the past becomes even less certain. Conquerors rewrite history to glorify themselves. Fires destroy libraries, erasing entire civilizations. Artifacts decay, leaving only fragments of stories that we're forced to interpret. Imagine a distant future civilization discovering the remains of our world. Will they believe our sci-fi movies were historical records? Will they think we worshipped superheroes and fought wars with laser swords? The past, it seems, is a puzzle we're constantly piecing together, but we can never be sure we're assembling it correctly. To deal with questions like these, philosophy offers a simple but powerful tool, Occam's razor. It tells us to prefer the simplest explanation that fits the facts. It's simpler to believe the pyramids were built thousands of years ago and still exist today than to believe the universe was created last Thursday with pre-aged pyramids and implanted memories. But Occam's razor isn't foolproof. Simplicity doesn't always mean truth. History is littered with obvious explanations that turned out to be wrong. And here's the uncomfortable truth. The past doesn't exist the way the present does. It's gone. You can't touch it, test it, or interact with it. All we have are records, fragile, incomplete, and biased. Think about it. Can you name 10 people from the 15th century? Millions lived, worked, and shaped the world back then. But most are forgotten, erased by apathy, time, or bad luck. And one day, the same will happen to us. But there's one part of you that will last forever, your contribution to the universe's entropy. Every breath you take, every step you make, every moment you live increases the universe's disorder. This is the one aspect of your existence that's permanent. No historian will perfectly reconstruct your life. No future archaeologist will fully understand your story. But the energy you've released into the cosmos will ripple out, unending and irreversible. The past, then, is just a story, a framework we use to make sense of the present. Whether the universe began billions of years ago or just last Thursday, one truth remains unshakable. You exist. Information hazards. The universe thrives on discovery. From the smallest particle to the vast reaches of space, humanity's relentless curiosity has unlocked countless secrets. Knowledge has been our greatest tool, propelling us forward, solving problems, and building civilizations. But not all knowledge is harmless. Some information, by its very nature, can be dangerous. These are called information hazards, and they challenge our belief that more knowledge is always better. An information hazard is a piece of knowledge that poses a risk simply by being known. Unlike physical dangers, like a wildfire or an earthquake, the harm doesn't come from something tangible. Instead, it emerges from the way the information interacts with minds, technology, or society. The most unsettling part. Some information hazards could have consequences on a global scale. Let's consider a simple example. Imagine learning the exact location of a hidden door to a bank vault. The knowledge itself might seem harmless to you, but in the wrong hands, it could lead to chaos. Now scale that up to something like discovering how to engineer a deadly pathogen or how to disable critical infrastructure. The information itself isn't dangerous in isolation, but it becomes hazardous when it influences the world in unintended or malicious ways. The problem is not just the knowledge itself, but how it spreads. Information is like a virus. Once shared, it's nearly impossible to contain. The more people know, the harder it is to predict the consequences. This becomes particularly concerning in the age of the internet, where a single leak can reach billions of people in seconds. A chilling type of information hazard is something called a decision hazard. This occurs when knowing something influences your behavior in harmful ways. For example, imagine you learn that a certain disaster is highly likely to happen in the next 10 years. That knowledge could lead to panic, societal breakdown, or even self-fulfilling prophecies, where people's reactions make the disaster more likely. One infamous thought experiment in this realm is Rocco's basilisk. The idea is that a future artificial intelligence might punish anyone who didn't help bring it into existence. Even considering the possibility creates a strange mental trap. If the AI becomes real, would you regret not acting sooner? While it's just a thought experiment, it highlights how certain ideas can twist our decision-making in unsettling ways. Then there's the existential threat of technological information hazards. Imagine if someone discovered the blueprint for a doomsday device, a machine capable of ending all life. Even if that knowledge was locked away, it could eventually fall into the wrong hands or inspire someone to build it. The mere existence of such knowledge is a risk we might not be equipped to manage. So, how do we deal with information hazards? Can we control what we learn or share? History suggests that suppression is nearly impossible. When people are curious, they dig. And when something is hidden, it often becomes even more desirable to uncover. Instead of suppressing knowledge, some argue that we need to focus on managing its spread and creating safeguards to mitigate potential harm. The challenge is walking the fine line between curiosity and caution. Humanity has always thrived by pushing boundaries, but we're now venturing into territories where a single idea could have catastrophic consequences. Information hazards remind us that knowledge is not inherently good or bad. It's the context and the way we wield it that matters. In the end, perhaps the best safeguard is awareness. Understanding the potential risks of certain types of information can help us approach discovery with responsibility and humility, because while the universe is full of secrets waiting to be uncovered, not every truth is one we're ready to face. Swamp Man. One day, deep in a remote swamp, something impossible happens. A bolt of lightning strikes the water, and by pure chance, it rearranges molecules into the exact configuration of a human being. Not just any human being, but an exact replica of you. Your body, your brain, your memories, your personality. This new being, let's call it Swamp Man, is indistinguishable from you in every way. It wakes up, stretches, and walks out of the swamp. It remembers your favorite songs, your childhood, the people you love. It feels like you, thinks like you, and even believes it is you. But is it really? This is the Swampman thought experiment, a puzzle introduced by the philosopher Donald Davidson in 1987. It's a strange and unsettling scenario that dives straight into some of the deepest questions about identity, consciousness, and meaning. At first glance, Swamp Man seems simple enough to categorize. After all, if it looks like you, acts like you, and thinks like you, then why wouldn't it be you? But as you dig deeper, the story starts to unravel, revealing profound philosophical problems. Let's start with the question of identity. If Swampman has your memories, skills, and habits, does that make it you? Or is there something else that makes a person unique? Something beyond physical matter and memories? Maybe it's your history, the specific experiences that shaped you over time, or the connections you've built with the world around you. Swampman doesn't have any of that. It only thinks it does. Its memories are a perfect copy, but they're not real. They weren't lived. So, is Swampman just an imposter? If you met Swampman, would it feel like meeting yourself? Or would it be a stranger wearing your life as a disguise? Now let's take this further. Imagine Swampman meets your best friend. It recognizes them, smiles, and starts a conversation about shared memories. Things it never actually experienced, but remembers in perfect detail. To your friend, there's no difference. They might laugh, tell stories, and never suspect a thing. But what about the deeper meaning behind those moments? Can Swampman truly connect in the same way you did? Or is it just mimicking the bonds you've built? This touches on a crucial question. Is meaning something that emerges from the process of living, or can it be replicated perfectly? If Swamp Man can act and feel like you, is it experiencing the world, or is it just running a program? This experiment also challenges the idea of consciousness. If Swamp Man has the same brain structure and neural activity as you, does that mean it's conscious? Or is it just a machine imitating thought? This question hits at the core of what philosophers call the hard problem of consciousness, the mystery of how physical matter creates subjective experience. If Swampman experiences the world like you do, it suggests that consciousness might be purely physical. But if it doesn't, then there might be something intangible, something irreducible about being alive. And what about morality? If Swampman isn't you, is it even a person? If you harmed Swampman, would it be wrong? Does it have rights, feelings, and autonomy? Or is it just an empty shell pretending to be human? Swampman leaves us with more questions than answers. It forces us to confront the limits of how we understand ourselves and others. It challenges the way we think about identity, experience, and connection. If there's one thing this bizarre thought experiment teaches us, it's that being human isn't just about what we are. It's about what we've lived, how we've changed, and the stories we share. Maybe that's the unsettling beauty of the Swamp Man thought experiment. It doesn't tell us who we are or what makes us real. Instead, it asks us to look deeper, to explore the fragile, intricate web of memory, experience, and consciousness that makes life extraordinary. And it leaves us wondering, if we ever met Swampman, would we even know? Would it? And in the end, does it even matter? You are walking through the ruins of a long-forgotten city. Crumbling towers rise into a grey sky, their foundations choked with vines. Dust hangs heavy in the air. Somewhere, distant echoes of a once thriving civilization whisper, "Why did it all end? And when will it happen again?" This is the doomsday argument, a thought experiment that suggests we might be far closer to the end of humanity than we realize. Not because of wars, plagues, or cosmic disasters, but because of math. The argument begins with a simple observation. We humans are just one link in the vast chain of existence. We're born, we live, we die, and the number of humans who have ever existed is enormous, over 100 billion by most estimates. But here's the twist. What if your position in this chain reveals how close we are to the end? Imagine numbering every human who has ever lived, from the first Homo sapiens to the last person who will ever exist. Somewhere in this list, there is you, right now. The doomsday argument assumes that your position in this list is random, not special, not chosen, just another point in the sequence. If that's true, then where you are on the list can give us a clue about how long humanity will last. Suppose we've already had 100 billion humans. If humanity survives long enough to produce, say, 1 trillion people, your position on the list becomes strangely lucky, like drawing a low number in a massive lottery. But if humanity's total population ends up being only a few 100 billion, your position feels typical. It's as if the universe is whispering, "You're closer to the end than you think." This reasoning is based on something called the Copernican principle, the idea that there's nothing special about your place in the universe. You're not at the center of existence. You're just one observer among many. By this logic, your position in humanity's timeline should be unremarkable. Not among the very first, not among the very last, just somewhere in the middle. So what does this mean for humanity's future? If we assume you're a typical human, then it's unlikely we're at the very beginning of humanity's story. More likely, we're somewhere in the middle, maybe even close to the end. According to some versions of the doomsday argument, this could mean humanity might only survive for another few centuries, or produce only a few more generations before vanishing entirely. But hold on. Could a simple math trick really predict the end of the world? Critics of the doomsday argument aren't convinced. They argue that humanity is not a random sequence of events. We shape our future, our population, our technology, and even our potential to survive catastrophes are influenced by our choices. Treating your position as random ignores the complexity of what makes us human. Others point out that the argument is based on shaky assumptions. What if you're not a typical human? What if the future holds trillions more people living across stars, planets, or even digital realities. In that case, your place in history isn't lucky, it's just early. So, is the doomsday argument a mathematical glimpse into humanity's future, or just an exercise in pessimism? Either way, it forces us to ask difficult questions. How long will humanity last? What should we do with the time we have? And, perhaps most importantly, what kind of future do we want to create? The doomsday argument isn't about despair. It's about awareness. If the possibility of an end motivates us to avoid it, then the argument has done its job. We can choose to see it not as a countdown, but as a call to action. In the ruins of that forgotten city, the whispers continue, but this time they're asking something new. If the end isn't set in stone, what will you do to shape the future? And if humanity's story is still being written, how can we make sure it's one worth telling? Boltzmann brains, you are sitting here, thinking, or at least you think you're thinking. Your mind processes the world around you, piecing together reality through the lens of memory, sensation, and reason. But what if none of it is real? What if you aren't real? What if you're just a Boltzmann brain? The Boltzmann brain thought experiment begins with a paradox buried deep in the laws of physics. To understand it, we need to step back to the 19th century, when physicist Ludwig Boltzmann revolutionized our understanding of entropy. Building on earlier work, Boltzmann gave entropy a deeper meaning, linking it to the microscopic world. He showed that entropy, the tendency of systems to move from order to disorder, was a matter of probability. Over time, everything, from a steaming cup of coffee to the vast cosmos itself, drifts toward chaos. But here's the strange twist. In an infinite universe, entropy isn't the whole story. Every so often, by sheer chance, particles can come together in just the right way to create a fleeting moment of order. Imagine a messy room suddenly tidying itself up on its own. Unlikely, yes, but not impossible, given infinite time. Boltzmann wondered if the universe itself might be the result of such a rare fluctuation. A chaotic cosmic soup, for one brief moment, arranged itself into stars, planets, and life. A stunning and improbable accident. But here's where it gets weirder. If random fluctuations can create an entire universe, they could also create something much smaller. Instead of billions of galaxies, what if the fluctuation produced just you? A fully formed consciousness, complete with false memories, sensations, and a sense of identity. A brain, floating in the void, imagining an entire universe that doesn't exist. This is a Boltzmann brain. The idea is unsettling because, on paper, it's far more likely for a random fluctuation to produce a single brain than an entire universe filled with trillions of stars. A Boltzmann brain requires less energy, less complexity, and if we follow the cold logic of probability, it's not only possible but inevitable that such brains should exist in infinite time. So how do you know you're not one of them? How do you know the world around you, the people, the sky, the ground beneath your feet, is real and not an illusion conjured up by a lonely brain drifting in the void? This thought experiment challenges everything we assume about reality. It asks whether the universe we perceive is truly there, or if it's a fleeting mirage, a statistical blip in an endless sea of chaos. It forces us to confront the fragility of what we call real. But does this mean we should throw our hands up and declare reality an illusion? Not necessarily. Many physicists push back against the implications of Boltzmann brains. They argue that a universe dominated by such bizarre entities would look very different from the one we observe. Our universe appears ordered and governed by consistent laws, suggesting that it's not a random fluctuation, but something deeper. Others propose that our understanding of entropy, time, or infinity may be incomplete. Perhaps the very framework that predicts Boltzmann brains is flawed, or maybe there's something fundamental about consciousness that prevents it from arising in such an improbable way. The Boltzmann brain thought experiment doesn't solve these mysteries. Instead, It invites us to question our assumptions. What do we mean by reality? What makes us certain of our experiences? And how do we navigate a universe where such strange possibilities exist? After all, real or not, this universe feels real to us. And maybe, just maybe, that's enough. Newcomb's paradox. You are standing in front of two boxes. Box A is clear and contains $1,000. Box B is opaque and its contents are unknown. You have two choices. You can take only box B, or you can take both box A and box B. Sounds easy, right? Obviously, you should take both boxes. After all, why leave money on the table? But here's the twist. Box B's contents have already been determined by a super intelligent predictor. If the predictor anticipated that you would take both boxes, it left box B empty. But if it predicted that you would only take box B, it filled it with $1 million. The predictor is almost never wrong. So, what do you do? Welcome to Newcomb's paradox, a thought experiment that pits logic against intuition and free will against determinism. It's a deceptively simple scenario with implications that stretch into the fabric of decision-making, game theory, and even the nature of reality. At first glance, this seems like a simple gamble. Take both boxes and you're guaranteed $1,000 from box A, plus whatever's in box B. But here's the catch. If the predictor knows you're going to take both, box B will be empty. If it predicts you'll only take box B, then it will be full. So, the real question is, do you trust the predictor's accuracy, or do you hedge your bets? There are two camps in this debate. The first is the one-boxers. They argue that the predictor is so accurate, it's almost like magic. If you take both boxes, you're practically guaranteeing that box B will be empty. The only way to walk away with $1 million is to commit to taking only box B. This camp sees the paradox as a test of trust in the predictor's near omniscience. If you can set aside your greed and take the leap of faith, you'll be richly rewarded. Then, there are the two boxers. They argue from a purely logical standpoint. By the time you're standing in front of the boxes, their contents are already determined. The predictor has either placed the $1 million in box B or it hasn't. Your choice won't change what's inside, so taking both boxes guarantees you at least $1,000. Why risk leaving money on the table? To them, the idea that your decision could influence a past event feels absurd. The paradox lies in the tension between these perspectives. On one hand, if the predictor is nearly infallible, your choice might as well be predetermined, making one boxing the only rational strategy. On the other hand, if you believe your choice has no bearing on the past, then two boxing seems like the clear winner. Both sides have compelling arguments, and no definitive answer exists. But Newcomb's paradox isn't just a quirky thought experiment. It's a playground for deeper philosophical questions. It challenges the nature of free will. If the predictor is always right, do you really have a choice? It also touches on causality. Can your decision in the present influence a prediction made in the past? And it's a fascinating test case for understanding how humans approach uncertainty and risk. Interestingly, Newcomb's paradox has real-world implications. It mirrors decisions in economics, politics, and even personal relationships, where trust and prediction play crucial roles. Do you trust the system and act in a way that aligns with long-term benefits? Or do you take what you can get right now, regardless of the consequences? In the end, Newcomb's paradox isn't about finding the right answer. It's about exploring how we think, how we decide, and how we grapple with the unknown. Whether you're a one-boxer or a two-boxer, the paradox invites us to question our assumptions about choice, consequence, and the nature of reality itself. So, which will you choose? One box or two? Chinese room. The Chinese room is one of the most famous thought experiments in philosophy, challenging our understanding of intelligence, consciousness, and what it means to know something. Imagine a room, a small enclosed space with a single person inside. This person doesn't speak or understand a word of Chinese, not even a little. But inside the room, They have a massive set of instructions, a rulebook written in their native language. Here's how it works. Chinese speakers outside the room slip written questions in Chinese through a slot in the door. Inside, the person uses the rulebook to match the shapes of the symbols on the paper with other shapes in the book. The rulebook tells them exactly which symbols to write down as a response, and they slip the answer back through the slot. To the Chinese speakers outside, the responses make perfect sense. It seems like the person inside the room understands Chinese fluently. But do they? This is the Chinese room, a thought experiment created by philosopher John Searle in 1980. It's not just about language, it's a thought experiment aimed at the heart of artificial intelligence. It asks, can a machine ever truly think, or does it just appear to think by following rules? Let's break it down. The person inside the room is like a computer. They don't understand the questions or the answers. They're simply following instructions, processing symbols based on predefined rules. The rulebook, meanwhile, is like the computer program. It tells the person exactly what to do, step by step. To the outside observer, it looks like the person inside understands Chinese, but in reality, they're just manipulating symbols without any comprehension. Searle's argument is this: even if a computer perfectly simulates human intelligence, answering questions, holding conversations, even passing the famous Turing test, it doesn't mean the computer actually understands anything. It's just following rules. It has syntax, but no semantics. It manipulates symbols, but it doesn't know what they mean. This distinction is crucial. Understanding involves more than just processing information. It requires consciousness, awareness, and subjective experience, qualities that machines, at least according to Searle, fundamentally lack. But not everyone agrees. Some philosophers argue that the Chinese room misunderstands the nature of intelligence. They suggest that understanding isn't something that happens in a single part of a system, like the person in the room, but in the system as a whole. In this view, the room, the rulebook, and the person working together form a kind of intelligence. If the system can consistently produce meaningful answers, then it might as well be called understanding. Others push back even further, claiming that human understanding is itself just a complex process of symbol manipulation. After all, isn't your brain a biological machine following its own set of rules? Maybe there's no magical difference between the person in the Chinese room and the neurons firing in your brain. Maybe understanding is just what happens when information is processed in the right way. Still, the Chinese room raises profound questions about the nature of consciousness. If machines can convincingly simulate understanding without actually understanding, how can we ever be sure another entity, machine or human, is truly conscious? Could a future AI be conscious in a way we can't comprehend, or would it just be an incredibly sophisticated Chinese room? And then there's an even bigger question. If understanding isn't necessary for intelligence, what does that mean for us? Are we, in some sense, also just rooms full of rules, responding to inputs with outputs based on our programming? Or is there something about human consciousness that goes beyond the rules, a spark that makes us truly alive? The Chinese room doesn't give us easy answers, but it does challenge us to think about what it really means to understand, to be intelligent, and to be conscious. As we move closer to building machines that seem more and more like us, these questions aren't just abstract, they're deeply relevant. Because if we ever build a machine that claims to understand us, we'll need to decide whether to believe it. Maybe, in the end, the Chinese room isn't just a test for machines, it's a test for us. To understand what we truly value in intelligence, and what it really means to be human. Pascal's mugging. Imagine this. You're walking home late at night when a stranger steps out of the shadows. But instead of asking for your wallet, they calmly say, "I'm a super intelligent entity from a parallel dimension. If you give me $100 right now, I'll use my vast powers to create a utopia where 1 trillion people live blissfully for eternity. Refuse, and nothing changes. I'll just disappear." Sounds ridiculous, right? Why would you believe such an outrageous claim? Yet, what if, just what if, they're telling the truth? The stakes couldn't be higher. This thought experiment is known as Pascal's mugging, a modern twist on an idea from the 17th century mathematician Blaise Pascal, who argued that you should believe in God, because the potential reward of eternal happiness outweighs the downside if you're wrong. But this updated version asks something deeper. How do you make rational decisions when faced with tiny probabilities and astronomical stakes? At first, the answer feels obvious. You'd laugh and walk away. The stranger's claim seems absurd, a baseless story without evidence. But here's where things get tricky. If the stranger is even 1 in a trillion likely to be telling the truth, the potential payoff, 1 trillion happy lives forever, still outweighs your small, finite loss of $100. It's basic math. Even a minuscule chance of such an enormous reward appears to justify the gamble. But wait, if you buy into this logic, you've just opened Pandora's box. What if another stranger appears and promises infinite happiness in exchange for $1,000? Or someone else demands all your money, claiming they'll save an infinite number of universes? There's no upper limit to how wild these claims could get. If you take one seriously, how do you decide where to stop? This is where Pascal's mugging really messes with your brain. It exploits the way humans think about probability and value. Normally we weigh risks and rewards based on what's likely and tangible. But when rewards are absurdly large, like trillions of happy lives, our usual rules break down. Even the tiniest chance of these rewards can dominate rational decision-making, leading to conclusions that feel deeply irrational. One way to deal with this is to reject the mugger's logic outright. You might argue that their claim is so implausible it doesn't deserve consideration, no matter the stakes. This is what philosophers call a prior probability, a way to say, some things are just so unlikely that they're effectively zero. But where do you draw the line? How do you justify ignoring tiny probabilities without ignoring real risks, like asteroid impacts or pandemics? Others propose redefining how we evaluate extreme scenarios. Maybe the problem isn't with the probabilities, but with how we calculate value. Do infinite rewards even make sense? Can we compare the happiness of 1 trillion hypothetical people to our own small, tangible lives? Pascal's mugging also reveals a troubling vulnerability in human reasoning. If we take its logic seriously, we could be exploited endlessly by anyone promising infinite rewards. But rejecting it entirely could mean ignoring genuine risks that could reshape the future. It's a paradox that forces us to confront the limits of logic, ethics, and even our sense of reality. So what should you do if the mugger appears? Hand over the $100 just in case? Laugh in their face and walk away? There's no clear answer. The thought experiment doesn't aim to solve the problem, but to expose how fragile our decision-making becomes when the stakes are unimaginably high. Maybe the real lesson of Pascal's mugging isn't about what's rational, but about humility. It reminds us that the universe is vast, our understanding is limited, and certainty is often an illusion. In the face of infinite possibilities, the only thing we can control is how we choose to respond. As the mugger waits for your answer, the real question is this: how do we navigate a world where the unimaginable isn't just possible, but might demand something of us? Eternal return. The universe is vast, mysterious, and filled with mind-bending possibilities. Among them is a truly strange idea: eternal return. Imagine a reality where everything, every star, every planet, every moment of your life is doomed to repeat itself endlessly forever. This isn't just a philosophical daydream. It's an idea rooted in ancient thought, modern physics, and a deeply unsettling question. What if you've already lived this life countless times before? And what if you're destined to live it again, forever? Eternal return challenges our basic understanding of time and existence. It proposes that the universe is cyclical, with every event repeating in an infinite loop. This means that somewhere, sometime, the exact moment you're experiencing right now has already happened, You've heard these words, felt these feelings, and made the same choices over and over for all eternity. The concept has ancient roots. Philosophers in India, Greece, and Babylon all flirted with the idea of time as a circle. But perhaps the most famous champion of eternal return was Friedrich Nietzsche. He didn't just suggest it as a possibility. He asked a provocative question. If this were true, would you celebrate it? Or would the weight of infinite repetition crush you? For Nietzsche, eternal return wasn't just about physics. It was a test of how you lived your life. If you knew you'd have to relive every decision, every success, and every failure forever, would you embrace your existence or despair at its inescapable monotony? From a scientific perspective, eternal return might seem far-fetched, but there's more to it than meets the eye. In an infinite universe, with an infinite amount of time, the odds of repetition aren't zero. Modern cosmology raises questions about the universe's shape and fate. If the cosmos were to collapse and re-expand in a series of big bangs and big crunches, a cyclical reality might not be so impossible. Even in a universe that expands forever, quantum mechanics tells us that particles can only arrange themselves in so many ways. Given infinite time, those arrangements might eventually repeat. But let's pause for a moment. If the universe repeats, does that mean you repeat? What makes you, you? Your memories, your choices. If your life were to play out exactly as it did before, are you still the same person? Or just a cosmic echo, endlessly reenacting a script you can't control? Here's where things get truly unsettling. If eternal return is real, does free will even exist? Are your thoughts and actions just part of a predetermined loop, the illusion of choice replaying forever? Or does the mere possibility of making new choices mean that the loop can be broken, giving rise to infinite variations? This thought experiment also raises a strange kind of hope. If life repeats endlessly, every moment becomes infinitely precious. Every hug, every laugh, every sunrise happens not just once, but an uncountable number of times. In this view, eternal return transforms existence from fleeting and fragile into something immortal, a tapestry woven from endless threads of the same moments. Yet there's also a darker side. For every joy, there is sorrow. Every triumph is shadowed by tragedy. And the idea of reliving pain, grief, and heartbreak forever can feel like a punishment more terrifying than death. In the end, eternal return isn't just about the nature of time or the universe, it's about us. It forces us to confront the value of our lives and choices. If every moment echoes into eternity, would you live differently? Would you take more risks, love more deeply, or savor the small wonders of existence? Perhaps the beauty of the idea lies in its paradox. Whether or not eternal return is true, it challenges us to imagine a life we'd be proud to live again, and again, and again. And in that challenge, it asks the ultimate question: can you make your life worth repeating?